Hi folks, we are continuing with the Unit 2 Day 1 lesson, and this is the second video. So I'm going to pick up where we left off at example number 2. So Sam here is pulling a sled with a rope. He's carrying his sister. He's pulling with a force of 275 newtons at an angle of 15 degrees to the horizontal. Determine the horizontal and vertical forces acting on the sled. So this is kind of the opposite of the last one. Instead of having two component forces and wanting to find the resultant, we are having the resultant be given, and we want to look at that and find the components. So feels like this is time for one of my terrible drawings. So here's his sister. And there's the rope, and here's my 15 degrees, and here's the kid pulling, and we have 275 newtons there. Okay, we can resolve this force into a horizontal and a vertical force. So some of his force is pulling upwards, but a lot of his force is pulling along this horizontal. So I'm just going to label F1 as horizontal and F2 as vertical. And I'll state kind of which one is which in the therefore statement. So this should be pretty easy. We know that horizontal and vertical have a nice right angle between them. So I'm just going to pull this away from my horribly messy, terrible picture. There is a reason I don't teach art, because that is about as good as it gets. And just redraw that as my right triangle. So here, I would use just SOHCAHTOA. A lot of people kind of forget SOHCAHTOA, I think, once they learn sine law and cosine law. You can use sine law here, but you really don't need to, because SOHCAHTOA is awesome and it still works great. So I would say sine 15 degrees is the magnitude of F2 over 275. Which gives me a vertical component of 71.18 newtons. And the cos will help me find F1. So cos 15 degrees equals the magnitude of F1 over 275. I don't really know why I did F2 before F1, but that's okay. So the magnitude of F1 is 265.63 newtons. So here, I really harp on this, that if you're looking at vectors, you need to remember magnitude and direction. Magnitude and direction, you need both. But we know that these are horizontal and vertical, so that's my direction right there. You don't have to find anything else there. So we can say, therefore, the horizontal force is 265.63 newtons, and the vertical force is 71.18 newtons. Okay. So again, almost all of this is just trig once you are able to kind of interpret the question and draw your vector diagram. Okay, this one is going to have an important use of our acceleration due to gravity. So here we've got a picture, and every year I kind of look at this and say, that is such a heavy picture. I don't know what the heck it's framed with, but I feel like I always look at that and say, that's too big, but never actually go back and change it. We've got a very heavy 15 kilogram picture hung from the ceiling by 2 cables. One cable, maybe this is it like in a gallery or something. One cable makes an angle of 35 degrees with the ceiling. The other makes a 25-degree angle with the ceiling. Find the tension in each cable. Remember, tension is a force. So, always start with a diagram. I've got a ceiling. Anybody I taught in grade 10, you'll remember I always say in these trig questions, always draw the ground, always draw the ground. If you've got a ceiling, draw the ceiling. So I have a picture. So there's some big, heavy picture. And it is hanging with 2 cables. I'm going to attach them right at the same spot, even though it doesn't say, just because I want a triangle. And one cable makes an angle of 35 degrees, and one makes an angle of 25 degrees. So we're not given any numbers about the amount of force. We don't have any measurements of force in here. So what we have to do here is thinking back to the force being mass times acceleration. So that's the force of gravity, is mass times acceleration. And we know that the mass is 15 kilograms times 9.8. So we can figure out what the force of gravity is. And that comes to 147 newtons. And that is always down. I'm just using a D, but you could write the word down there too. So I know that I have a force of gravity acting on this object, and I'm gonna kind of squeeze it in a different color so it stands out a bit. So somewhere acting on this object, I should have left it a bit more room, but force of gravity is going down. Now, presumably, this picture hanging on the wall in an art gallery or somewhere is not moving. If the picture is getting like ripped out of the wall and falling because the force of gravity is so big, that's a bad art gallery. We want to make sure that there's an equal force, an equilibrium force, keeping the picture up. So we can assume that there's some force in this cable and some force in this cable that's balancing out this force of gravity, that there's an equilibrium force. Remember, it has to be in the exact opposite direction. So we know that there's going to be a force in the first cable, and I'm going to call that T1. Instead of F1, I'm going to just call it T for tension, because we know it's the force of tension. And there's going to be one in this cable. And I know that the force of gravity is going to be going straight down, so that there must be an equilibrium force going straight up. That these two will balance each other out. Now, the only place this equilibrium force could come from is from the tensions in the wires. Now, see, if we added up T1 plus T2, it's going to, like, kind of, you can see that these two red vectors would add up to the equilibrium. So they're going upwards. So I have an equilibrium vector pointing directly opposite from gravity, and I have these two tension that are in the wires, and we know the angles of the wires. So we can put this all together, and let me redraw this diagram here. That I have T1 and T2 And I know that the magnitude of the equilibrium has to be equal, because this is not moving, to 147 newtons. So I can find force of gravity. I know the picture is not moving, so there must be an equilibrium. And then these two guys must add up to that equilibrium. The other tricky thing in this question, oftentimes people have trouble with the angles. And there's a lot of ways of looking at this. I'm going to go back to my original picture. If I drew my equilibrium in here, right there, going up, hopefully if we draw that vertical line, hopefully you guys can see that this angle in here would have to be, that would have to be a 90-degree triangle, so that down here would be 65 degrees. So I'm going to take that same 65 and label it in there. Right? Now, kind of the same reasoning, this would be 55 degrees in there. So I'm going to label that up there. And then there's a few different ways of looking at this, I think, and this might be a little bit of overkill with the colors here, but I think that a lot of people will most easily see that this is a Z pattern, because this was the direction of T2 in that other wire, and kind of subtracting, make two 90-degree triangles to find out those base angles. Then you'll see the Z pattern would leave you that 55 up at the top. There's other ways, absolutely, of looking at this, but that I think is the most common one to make sense to the most people. However you're able to get those angles, it's just kind of a combination of the things you've known for a long time. All the angles add up to 180, Z pattern, C pattern, parallel lines. It's like there's no magic to it. It's just kind of how you draw it and how you look at it that makes the most sense to you. So this has gotten, again, kind of a diagram gets messy and I keep drawing a new one. 147 newtons here, and this is 65, and this is 55. And here I have T2 magnitude and T1 there. Okay? So we're going to have to find the magnitude of each tension, and that's going to be with the sine law. So I will figure out that biggest angle. So what am I doing here? Yeah, sorry, here we've got, no, not biggest angle. This is a 60-degree angle when we subtract from 180. So we've got sine law. We can find the magnitude of T1 over sine 55 is 147 over sine 60. So here I get 139.04 newtons, and then I'll do the same for T2. So the magnitude of T2 over sine 65 is 147 over sine 60. And this one's 153.84 newtons. So these, again, the tensions are vectors. We do not actually have to find direction for these ones because we know the direction is in the cable. So that is the direction. It's along the cable can be the direction, but you have to state that. So therefore, the tension in the, so my T1 was the one at 25 degrees. The is 139.04. And the tension in the 35 degree cable is 153.84. Both of those newtons. So this description, the tension in this cable, means that that is your direction. So I am giving a vector quantity of a magnitude and a direction. The direction is in along this cable that's anchored at a 25 degree angle. So that tends to be one of the trickiest ones, and it's mostly the setup. These are all fairly similar. If you find the gravity, create an equilibrium, and draw your triangle. Some of this with the finding the angles tends to be the trickiest part in this type. This one's kind of a more theoretical question. Is it possible for three forces of 15 newtons, 18 newtons, and 38 newtons to keep a system in equilibrium? So basically for all of those forces to add up. And you know what? I'm just going to leave that. It is not, but I would like you to think that over, and I will include it in the solutions, but I'd like you to kind of give that some thought about why it would not be possible. And the last example here. So a 30 kilogram crate sits on top of a ramp, or on a ramp inclined at 20 degrees. Calculate the parallel and perpendicular forces because of gravity acting, or the parallel and perpendicular forces because of the gravity on the crate that are on the ramp. Okay. So again, always draw your diagram. I've got a horizontal floor. Then I have a ramp that's inclined at 20 degrees. I have a crate sitting on the ramp that weighs 30 kilograms. I'm going to go ahead down here. Whenever you see that weight and you don't have any forces, we're going to find the force of gravity, which is 30 times 9.8. So it's 294 newtons. Now, the trick with things on ramps is that I think a lot of people want to draw gravity going that way. And because that's kind of what it's sitting on, gravity, like there's kind of an instinct to draw gravity like that because it's being held down. But that's not how gravity works. Gravity always goes straight down. So you're never going to, whoops, shaking my camera here. You're never going to draw gravity any other way except straight down. So I'm going to draw the force of gravity going straight down. Now, if this crate is not moving, what are the component forces that would be acting against that? Or another way of thinking about this, and you could, it's going to kind of end up being the same either way. What would the forces pulling this down the ramp be? So some of gravity is going to be coming down, but some of the force of gravity would be going like this. So if we want to make it component forces that are parallel and perpendicular to the ramp. So I'm going to draw this force here and this force here, and these are the component forces of gravity. So there must be opposite forces of these if it's not moving, but it doesn't actually specify that. If this was not moving, so if this was in equilibrium, there would be component forces, something probably friction going up the ramp, and that normal force acting upwards here. But I'm going to label this F1 and F2. And again, the really tricky thing in here is just getting your angles. Because we know that if this is parallel and perpendicular to the ramp, that's going to be a nice 90 degrees. We just have to kind of analyze this a little bit and see if we can figure out what that other angle would be. And I think that it should be kind of with how I've drawn this. I think that you guys should be able to see this. If we have this gravity, we know that the gravity is acting perpendicular to this kind of flat ground, and that the ramp is at an angle going up there of 20. So hopefully, kind of looking at this, that this would be parallel here, that this angle in here will be 70, and this is going to be the same up there. So that's 70 degrees up there. You can see that these are parallel lines cut by a transversal, so I guess that's like an F pattern in there. So we've got this force of gravity going down, and we have our two component forces of gravity, F1 and F2, that are parallel to the ramp and perpendicular to the ramp. And I know that that angle there is 70. Some people sometimes do a different kind of reasoning to show that this is 20, and that's fine too. However you're able to kind of show it, just make sure you label your angles on your diagram. So once we get there, we're all set. We know that the force of gravity is 294. And then we're just going to use SOHCAHTOA to find the magnitude of F1 and F2. So here we get cos for F1. So cos of 70 is the magnitude of F1 over 294. So the magnitude of F1 is 100.55 newtons. And then sine of 70 is the magnitude of F2 over 294. So the magnitude of F2 ends up being 276.27. Okay. Now we want to write our therefore statement. Again, we know the direction. We have to include magnitude and direction, but we know the direction. We don't have to solve for that. We know that F1 is parallel to the ramp and F2 is perpendicular. So we could say, therefore, the force of gravity is 100.55 newtons parallel to the ramp, and 276.27 newtons perpendicular to the ramp. So if this object was not moving, then we would know that there would have to be equal but opposite direction forces, those equilibrium forces that might be a force of friction, most likely going up the ramp, and a normal force that would counteract that F2 being applied because of the contact with the crate and the ramp. And that is it for Unit 2, Day 1.